that being said, you can see me right up here in the little corner. The bizarre news story of the day. Jupiter apparently eats other planets. So this is an article that was sent to me by one of my friends. Well, not sent to me, sent in a group chat. I was in the group chat. And interesting take on things. So kind of what this article says, all things considered, Jupiter seems like a pretty scary place. More than 300 times bigger than Earth, the king of planets has double the strength of our gravity and an exceptionally dense, dry atmosphere. Some scientists now reckon that Jupiter could have been even more beastly than we previously thought. An article in the Journal of Astronomy and Astrophysics says that the planet may have become its ginormous, monstrous self by eating other planets. Paper suggests Jupiter has the remain of other planets inside of it. Although the theory that Jupiter is born out of other planets has been around for a while, a clearer picture was revealed after the planet's infamous gases temporarily parted and NASA's Juno space probe was able to get some data about its core. Very cool, very lucky for that Juno mission. And it goes on a little bit to talk about kind of the making of Jupiter, and I ultimately believe that this is why that it's so important, because kind of hard to, you can look at kind of what the atmosphere is made out of and kind of guesstimate what elements are in the atmosphere and kind of see what possibly the core could be made out of. I think there's other ways to do it with telescopes. Once again, folks, if this is your first time listening, I'm not an expert on this. I'm an enthusiast. And I try and get my very basic knowledge that I got from taking basically 3 years of astronomy courses. No physics courses, did not take any physics courses, but I took astronomy courses. So my knowledge on this is pretty much base level. I just am enthused about this kind of stuff. I find it interesting. With that being said, I want to go back over and share the screen and talk about this paper as well, because I do think it is interesting, and I think it is a cool thing to talk about. I mean, the idea that there's a planet in our solar system. Now, if you are aware, the early solar system of ours, where Earth, before it had life, although there is some talks about life being billions of years old, maybe coming like maybe like 3+ billion years old. Some people have said that there's evidence of that. I'm not sure. It's something I only just saw it in passing, and I didn't want to talk about in length because I just didn't know too much about that subject. But with this, I think it does tie into kind of the early universe and how Jupiter was basically the protector. And that's something I definitely am going to try and portray over here as we go over to this secondary window. Let me get my cursor over here. There we go. Jupiter's inhomogeneous envelope. This is in the astronomy and astrophysics. And then let me go back to that first article. First article, to shout them out, timeout.com, bizarre news story of the day. Jupiter apparently eats other planets. That's the name of the article, written by Ed Cunningham. So make sure you go check that out. And now let's go back over to the astronomy and astrophysics. This is the study that they did talk about in the article, posted in June 2022. Bunch of different authors on this. So received January 27, accepted in March, and then just posted. So let me just read the abstract context. While Jupiter's massive gas envelope consists mainly of hydrogen and helium, the key to understanding Jupiter's formation and evolution lies in the distribution of the remaining, in quotes, heavy elements. Before the Juno mission, the lack of high precision gravity harmonics precluded the use of statistical analysis and a robust determination of the Halley element distribution in Jupiter's envelope. This is going to be a little tough for me to understand because this gets really technical, really technical. Moving onwards, aims. In this paper, we assembled the most comprehensive and diverse collection of Jupiter interior models to date and use it to study the distribution of heavy elements in the planet's envelope. Methods. We apply a Bayesian, Bayesian statistical approach to our interior model calculations, reproducing the Juno gravitational atmospheric measurements and constraints from the deep zonal flows. And then the results. Our results show that the gravity constraints lead to a deep entropy of Jupiter corresponding to a 1 bar temperature that is 515 Kelvin higher than traditionally assumed. We also find that uncertainties in the equation of state are crucial when determining the amount of heavy elements in Jupiter's interior. And then it continues on. Furthermore, we robustly demonstrate that Jupiter's envelope is inhomogeneous with a heavy element enrichment in the interior. This implies, inhomogeneous with a heavy element enrichment in the interior relative to the outer envelope. Interesting. This implies that heavy element enrichment continued through the gas accretion phase, with important implications for the formation of giant planets in our solar system and beyond. So I think they're talking about when Jupiter was in its so-called creation, as it was forming. Yeah, kind of looking at the introduction. If you are watching this, read the introduction as well. Once again, folks, this is a pretty technical article, and I reading over this, I had a hard time trying to decipher it, but I just wanted to show that this is the article that they are referencing. So it does talk about the kind of the birth of the planet of Jupiter, and as you can see here, they kind of talk about how the core of it is actually different from what they had expected. Let's go to this picture right here. The year one. You can see the difference in the atmosphere. So you have, if you're watching this on the A model, you have, I think this is dihydrogen. Once again, helium poor, and then zinc, I believe. Mono zinc, I believe. I don't know, folks. I'm a little bit out of my element right now. I'm not gonna lie to you, but this is just kind of looking at what their core of the planet is from what they've been able to gather around and look at. And then we got a bunch more gravity stuff and how gravity played an effect, results. All of our models reproduce J2 and Jupiter's radius. Okay, a bunch more stuff that I really don't know. I want to read the conclusion though. This study comprehensively reproduces observational constraints from the Juno measurements along with helium measurements from the Galileo probe, exploring different models for Jupiter's interior and considering all recent equations of state. We showed that the gravity constraints point to a deep entropy of Jupiter that corresponds to a 1 bar temperature that is higher than traditionally assumed. We robustly demonstrate that the heavy element abundance is not homogeneous in Jupiter's envelope. Our results imply that here's the thing. Our results imply that Jupiter continued to accrete heavy elements in large amounts while its hydrogen and helium envelope was growing, contrary to prediction based on the pebble isolation mask in its simplest incarnation. Interesting. Interesting, interesting. Furthermore, the envelope did not mix completely during the planet's subsequent evolution, not even when Jupiter was young and hot. So kind of what the I guess kind of what I was able to take away from this was that in the beginning of Jupiter, as it was slowly building, it was slowly gaining mass and beginning to come to a certain point where it was actually able to form a core and then form a what's the word I'm looking for? No, I guess they use envelope, but I when I think of that, I think of atmosphere. I guess I'll just call it atmosphere, but I think when you do look at things like this with Jupiter and kind of how big it has become and how much of an impact it has had on the universe as a whole, really important to kind of know how it was able to start and if it was able to. I mean, based on what they are saying in this piece, is that they are able to find that there are things kind of that were brought in, the heavy elements, things that you most likely would not see just out and about. It would mean that something would have to go into Jupiter's orbit and be a little bit eaten up by Jupiter in order to get that, because you're not going to be able to create that out of nothing, obviously. So I guess kind of the idea in this is that when you are early in the stage, such as Jupiter, I don't know if they're going to extrapolate this out, but I think in this case, what they are saying is that big giant planet like Jupiter early on was able to get a lot of its mass because it was able to get heavy elements from objects in its vicinity around it, which could possibly mean other planets that might have been in the solar system that were close to Jupiter and over a period. I mean, this could be billions of years, this could be millions of years of time in which it took for them to orbit around the sun, for them to most likely collide, and then Jupiter ultimately take a lot of the heavy elements from that smaller planet. I think that's kind of what this is talking about. Because one funny thing that I saw is this right over here. One thing is Jupiter is pretty big. According to Newton's law of universal gravitation, Jupiter pulls you 34 million times less than Earth pulls you down. And then here's the other thing I wanted to talk about. By deflecting comets and asteroids that might otherwise hit Earth, Jupiter has helped to create a more stable environment for life to evolve here. And it talks about 65 million years ago, asteroid that took out the Earth. I think that is part of the importance of this specific paper that came out, and the reason why maybe there was another planet that was here and it was able to impact with Jupiter very early on in the timeline of our solar system. And maybe it was able to suck some stuff up, Interesting stuff. Interesting stuff. And then